Okay, so now that you've had some time to read through the problem, let's walk through it together. I'll take you through the thought process and coming up with the algorithm, and hopefully you'll understand it well enough to do the proof of correctness and runtime analysis by yourself. So here we essentially have a variant of the max flow problem. We have a directed graph, we have integer capacities on the edges, and a source. The only difference is that we have two sink nodes instead of just one. And we want to maximize our total flow into the two sinks, but we want to ensure our flow is fair, or like the value of the flow into one sink is at most one more than the value of the flow into the other. And because this problem is so similar to traditional max flow, we can try to come up with an algorithm that's very similar to Ford-Fulkerson, where we create like a residual graph and try to find an augmenting path. And we just need to make sure that we meet the fairness constraint. And so at any given point when you're running our algorithm, assuming we're meeting the fairness constraint along with the other constraints of like a traditional network flow, such as like flow conservation and meeting like the edge capacities, there are three possibilities for our current flow F. So our first possibility would be if the flow into T1 is the same as the flow into T2. Second possibility is if the flow into T2 is one more than the flow into V1. And our last possibility is just the other way around. Okay, so these are our three possibilities, assuming that we're meeting the fairness constraint at all times during our algorithm. And so for the first possibility, if we want to increase our flow by augmenting along a path, we can either send one unit of flow along an ST1 path or one unit of flow along an ST2 path and still meet the fairness constraint. But for the second possibility, if we were to send a unit of flow along an ST2 path, then the flow into T2 would be 2 more than the flow into T1, which violates our fairness constraint. And so we must send a unit of flow into T1 or along an ST1 path, and so then that will make the flows equal into the two sinks. And so the third possibility will just be the other way around. We must send a unit of flow into T2, so find an augmenting path along an ST2 path. Okay, so this is very much like Ford-Fulkerson, except instead of augmenting by the minimum capacity of our edges in our ST path in like our residual graph, we augment by a flow of 1 instead. Okay, so now we can try building the rest of the algorithm, and I'll just use the graph that was given to us in the problem as an example. So to create a residual graph, we need to have an initial flow in the first place. And we want to meet the fairness constraint, so we can start by sending one unit of flow along either an ST1 path in our graph G or an ST2 path, since there's like no flow originally. But I'll just send one unit of flow along this ST1 path. And so now we have to create our residual graph. Okay, so here's our residual graph. And right now, V1 is one more than our V2. And so that means we need to search for an ST2 path along our residual graph. And we can see that we have one right here. So we want to augment one unit flow along that path in our original graph, G. And so the flow of both of these will become 1. And so now the flow into both T1 and T2 are 1. And so we have V1F equals V2F. And so during this next iteration, we can augment along either an ST1 path or an ST2 path. And so now I have to consider, when do we stop? When does our algorithm end? Okay, so if we have V1F equals V2F, we can keep going as long as we can find either an ST1 path or an ST2 path in our residual graph. And we want to keep on going because we want to maximize our flow. So we will continue going until we can't. But if we have V1F being 1 less than V2F, we can only keep on going if we can find an ST1 path. Because again, if we were to augment along an ST2 path, then our flow into T2 would be 2 more than our flow into T1. And so we stop if we can't find an ST1 path in our residual graph. And similarly, if we have V2F being 1 less than V1F, we stop if we cannot find an ST2 path. And so that's the final flow F we end up with, and that's what our algorithm returns.